All right, let's dive into this like deep dive into Stephen Hawking's A Brief History of Time.
Okay.
Um, this book, I mean, it wasn't just some science book, you know? This was a bestseller,
Yeah.
a huge one.
Huge.
So, what does that tell us? It tells me, at least, that there are a lot of people out there who are just curious about the universe. Where did it come from? How does it all work, you know?
Right.
And Hawking, in this book, really tries to explore those questions, those big questions. And we're going to unpack it all, from relativity to quantum mechanics to the Big Bang.
I think one of the things that really struck me about this book was how Hawking takes these concepts that are really complex
Yeah.
and he makes them, I don't know, accessible. You know what I mean? Like he invites you on this journey to kind of understand the universe a little bit better.
He does. And I love how he starts it off, too, with that anecdote about the scientist who's trying to explain the universe
Yes.
to this little old lady who's convinced that the world is flat and that it's sitting on a giant tortoise.
Oh, yeah. It's turtles all the way down.
Yeah.
I love that
It's
part.
turtles all the way down. It's just brilliant.
So good. So good.
It's such a perfect way to kind of start the book because it shows us how our picture of the universe, it's changed, right? It's changed so much over time.
Totally.
Yeah.
Like for a long time, people really thought that the Ptolemaic system, with the Earth at the center
Right.
was just, that was the way it was.
Yeah, that Earth-centric view, everything revolving around us, like we're the center of the universe.
It does have a certain, appeal to it.
It does. It's cozy,
Right.
you know.
It's, nice and tidy. And, the church really liked it back then, too, because it left room for heaven and hell.
Yeah, it all kind of fit together.
Right.
Science and religion, it all worked. But even Ptolemy himself knew that his model wasn't perfect.
Yeah.
It predicted that the moon should sometimes appear twice as big,
Yeah.
which obviously wasn't happening.
Obviously, no.
So then Copernicus comes along in the 16th century and proposes a radical idea. He's like, what if the sun is actually at the center?
Right.
Right. And the Earth and all the other planets are revolving around it.
Yeah, completely flip the script.
It was a total paradigm shift.
Yeah.
And that heliocentric model, it started to gain traction because of guys like Kepler, who figured out that planets move in these elliptical orbits.
Yeah.
And Galileo, who built this telescope.
With his telescope.
And was making all these observations that just totally blew the Earth-centered view out of the water.
Yeah, it was like, wow, we're actually not the center of the universe.
Right. And then, of course, along comes Einstein in the 20th century, throws general relativity into the mix.
Mm-hmm.
And suddenly gravity is not just a force anymore. It's like a warp in the fabric of space-time.
Mind-blowing.
Mind-blowing, right.
Yeah.
And then you have quantum mechanics, which governs all these tiny particles and how they behave.
The subatomic realm, yeah.
So you've got general relativity, which is like the big stuff, the universe on a grand scale. And then you've got quantum mechanics, which is like zooming in on the tiniest bits of reality.
Exactly.
But here's the problem, and this is what Hawking highlights, is that these two fundamental theories,
Yeah.
they don't play nice together.
They do not play nice.
They clash.
That's a really great way to put it. They clash.
It's like you've got these two sets of rules that work perfectly in their own domains, but when you try to put them together, it just falls apart.
Right. It's like a cosmic puzzle that we're still trying to solve.
And it has been,
Yeah.
It's been driving physics research for decades now. So we've got these two pillars of modern physics, and they both lead to some really mind-bending ideas about space and time.
Totally.
Right?
Totally.
I mean, one of the key insights of Einstein's special relativity is that the speed of light, it's constant for all observers. Doesn't matter how fast you're moving.
That is wild.
Yeah, you would think, right? Like if you're moving towards a beam of light, it would seem faster.
It makes sense, yeah.
Nope.
Not how it works.
It always travels at the same speed.
Yeah. Blows your mind, doesn't it?
But that kind of messes with our everyday sense of time and distance, right? If the speed of light is always the same.
It really does. It means that our intuition about time, time is this universal clock ticking away at the same rate for everyone, that's just not true.
Right.
It's wrong. Time is relative,
Yeah.
and it's all intertwined with space.
This whole space-time concept. So instead of thinking of space and time as separate things,
Yeah.
we need to think of them as this unified fabric, this sort of four-dimensional thing, right?
Yes, it's like upgrading from a two-dimensional map to a three-dimensional model, but even better.
Okay. And to pinpoint any event in space-time, you need not just 3 coordinates like you would for a location in space, but 4 coordinates, including time.
That's right, you got to add that time element in there.
So it's like every location gets a timestamp. So My morning coffee,
Oh.
my afternoon walk, my evening Netflix binge.
All points in this four-dimensional space-time continuum.
Whoa. Okay,
Hmm.
so to understand how all these events in space-time relate to each other,
Yeah.
Hawking uses this brilliant concept of light cones, right?
Yes. Light cones. So cool.
So imagine you throw a pebble into a pond.
Oh, okay, I'm imagining.
What happens, you get these ripples, right? They spread out in
The
circles
bandy circles.
from where the pebble hit the water. Now imagine those ripples, they're not just spreading across the surface, but they're also going upwards,
Okay,
creating a cone shape.
I see it, yeah.
That's your light cone.
Right,
The tip of the cone, that's the event, like the pebble hitting the water.
right.
And then the expanding cone, that represents how light or any information travels outwards from that event through space and time.
You got it.
And here's the thing.
Yeah.
Events inside the light cone, they're connected. They can influence each other. But events outside the cone, they're in the elsewhere. They're too far away in space or in time
Right.
to have any causal relationship.
It's like they're in their own little bubble.
It's like a cosmic speed limit
Yeah,
set by the speed of light.
exactly.
If something's outside my light cone, it might as well be on another planet in another galaxy.
Right, there's just no way for them to interact. It highlights how interconnectedness is determined not just by distance, but also by time.
Okay, so light cones are like these bubbles of causality in space-time.
I like that, yeah.
Everything inside can interact, but outside it's like a separate universe. This is getting pretty deep. So where do we go from here?
Well, special relativity, as revolutionary as it was, it had a big limitation. It didn't include gravity.
Oh, right.
And it actually seemed to imply that gravity would act instantaneously, which would mean it could travel faster than the speed of light.
Which, wouldn't that contradict the whole theory itself?
Exactly. Einstein knew this was a problem and spent years trying to figure it out.
So Einstein's own theory was pointing to a flaw. That's gotta be tough.
Well, I'm sure it was an intense struggle. But eventually, he had this amazing breakthrough. He realized that gravity isn't a force in the traditional sense, but it's a consequence of the curvature of space-time itself.
Wait, hold on. Gravity is a curvature in space-time. You're gonna have to explain that one.
So picture this.
Yeah.
You've got a bowling ball sitting on a trampoline.
Okay, I'm picturing it.
It makes a dip in the fabric, right?
Yeah.
That's kind of like what massive objects do to space-time. They warp it, they create these curves, and that warping, that's what we experience as gravity.
So it's not that objects are pulling on each other. It's more like they're following these curves in space-time.
Exactly. It's not a force, it's geometry. Pretty wild, huh?
That is wild. Okay, so if light travels through space-time and space-time is warped, does that mean light itself can bend?
You got it. That's exactly what general relativity predicts.
Wow.
And it was actually confirmed back in 1919 during a total solar eclipse.
Really?
Yeah, astronomers were able to observe that starlight passing close to the sun was deflected just a tiny bit.
Oh,
But it was enough to prove Einstein right.
so they actually saw this bending of light.
They did, and it matched Einstein's calculations perfectly, or pretty darn close anyway.
That's pretty convincing evidence.
It is.
But wait, it gets even weirder, right?
Oh, yeah.
Didn't Einstein also say that gravity affects time?
He did. That's one of the most mind-boggling things about general relativity. Time itself is warped by gravity. The stronger the gravitational field, the slower time runs.
So, like, if I was hanging out near a black hole, time would move slower for me than for someone back on Earth.
Exactly.
I would literally age more slowly.
That's the idea behind the twins paradox. You have one twin who goes on a super fast space voyage, experiencing all the strong gravity, while the other twin stays on Earth.
Right.
When they meet up again, the traveling twin is younger.
That is just why it's like something straight out of science fiction, but it's real.
It is. It's one of the strange but true consequences of Einstein's theory.
So general relativity gives us all these crazy insights into gravity, space-time, even time itself.
It does.
But what about the big picture? You know, the evolution of the universe. Where does the Big Bang fit into all of this?
Well, one of the things that comes out of general relativity is the idea that the universe can't be static. It has to be either expanding or contracting. And that prediction actually led to the development of the Big Bang theory.
Oh, okay.
It all started with observations of starlight, actually.
Oh, right. Now, I remember reading about the Doppler effect.
Yes, The Doppler effect.
It's like when an ambulance siren sounds higher pitched when it's coming towards you and then lower pitched as it moves away.
Exactly.
That change in pitch, that's because the sound waves are getting compressed or stretched out as the source moves.
Exactly. And the same thing happens with light waves.
Oh, interesting.
Light from a source that's moving towards us, it gets shifted to shorter wavelengths,
Okay.
toward the blue end of the spectrum. But light from a source moving away, that gets shifted to longer wavelengths, towards the red end, red shifted.
So if a galaxy is moving away from us, its light would be red shifted. Yep.
And in the early 20th century, astronomers started to notice something really interesting.
What's that?
They found that light from distant galaxies was red shifted.
Huh.
And the farther away the galaxy, the greater the redshift.
So does that mean we're at the center of the universe and everything's moving away from us?
Not quite. It's not that we're special or anything.
Okay.
What's happening is that the fabric of space itself is expanding, and it's carrying the galaxies along with it.
Oh.
It's like if you imagine dots on a balloon.
Right.
As you inflate the balloon, the dots get farther apart.
Yeah.
But there's no one dot that's the center.
Oh, I get it. So it's like the universe is this giant expanding balloon, and the galaxies are just riding along on the surface.
Exactly. That's a great way to picture it.
Okay, so this whole expanding universe idea, how did that lead to the Big Bang Theory?
Well, if you imagine running the cosmic film in reverse, rewinding the expansion,
Okay.
it means that everything must have been much closer together in the past. Keep rewinding, and eventually you get to this incredibly hot, dense state, a singularity. That's the Big Bang.
Oh, it's like tracing the universe's family tree back to this single ancestor.
Exactly. Now, the Big Bang Theory got even more support in the 1960s with this accidental discovery: cosmic microwave background radiation.
Wait, they stumbled onto evidence for the Big Bang by accident?
They did. It's a great story, actually. These two physicists, Arno Penzias and Robert Wilson, were working on a new antenna, a really sensitive microwave antenna.
Uh-huh.
And they kept picking up this annoying background noise.
Oh, no.
They tried everything to get rid of it. They even checked for pigeon droppings in the antenna.
They thought pigeon droppings were messing with their experiment. That's hilarious.
It is. But it turned out that this noise wasn't coming from anything on Earth. It was coming from every direction in space.
Wow.
And it was the faint afterglow of the Big Bang itself.
So they accidentally detected the echo of the universe's birth.
They did. And this radiation they found, it perfectly matched what physicists had predicted this afterglow should look like.
Wow, that's incredible.
It was a huge confirmation for the Big Bang Theory.
So we've got the expanding universe, this cosmic background radiation, and the idea that it all started from this super hot, super dense state. But what did the Big Bang itself actually look like? What happened in that very first moment?
Well, that's where things get a bit tricky. Hawking dives into the work of this physicist, Alexander Friedmann,
Okay.
who used Einstein's general relativity to model an expanding universe.
Right.
And all his models pointed back to this initial point, a singularity. Infinite density, infinite temperature.
So the Big Bang was like this infinitesimally tiny point containing everything that would become the universe.
In a nutshell, yes.
Wow.
But the singularity, it presents a huge problem.
What do you mean?
Well, the laws of physics, as we understand them, they just break down at that point.
Oh.
We can't describe the very beginning of the universe using our current understanding.
So it's like hitting a wall, a cosmic wall.
Exactly. We can get really, really close, like a tiny fraction of a second after the Big Bang. But that very first moment, it remains a mystery. Now, there were other theories out there, like the steady state theory,
Okay.
which said that the universe had no beginning and that matter was continuously created to maintain the density as it expanded.
So like an ever-flowing river, always changing, but always looking the same.
That's a good way to put it. But the steady state theory ran into problems, especially after the discovery of the cosmic microwave background radiation.
Right, because that wouldn't exist if the universe had always been the way it is now.
Exactly. Now, another important piece of this puzzle is the work of Roger Penrose. He showed mathematically that when a star collapses,
Okay.
it would inevitably form a singularity,
Oh.
a point of infinite density. And this idea of a singularity at the heart of a collapsed star, that's what led to the concept of black holes.
Black holes, yeah. Those regions of space-time where gravity is so strong that nothing can escape.
That's right, not even light.
They sound terrifying.
They are fascinating, that's for sure. And Hawking uses this personal anecdote to illustrate how our understanding of black holes has evolved.
No.
He talks about himself, getting into bed one night, which was a slow process for him because of his disability, and he was thinking about black holes.
It's amazing how those big thoughts come to us sometimes, in the quiet moments.
Right. And as he was thinking about black holes, he had this realization, maybe they aren't as black as we thought.
Wait, how can a black hole not be black?
Well, the defining feature of a black hole is its event horizon.
Okay.
That's the boundary beyond which nothing can escape.
So it's like a point of no return.
Exactly. But here's the thing. Classical physics tells us that black holes should have no entropy.
Entropy, that's a measure of disorder, right?
Right. And if they had no entropy, it means they wouldn't have a temperature. But any object with a temperature should radiate energy.
So you've got this conflict. Black holes shouldn't radiate anything, but if they have a temperature, they must radiate energy. How did Hawking solve that?
Hawking brought quantum mechanics into the picture.
Ah, okay.
He realized that even in empty space, there's this constant fizz of virtual particles.
Virtual particles?
Yeah, they kind of pop in and out of existence.
That's kind of spooky.
It is a bit strange, but they have real effects.
Huh.
Hawking said that sometimes one of these virtual particles might appear right on the edge of a black hole's event horizon.
Right on the edge.
And then one particle gets sucked in while the other escapes.
So it's like a cosmic coin toss.
Yeah, like a game of chance.
One particle gets lucky, the other one not so much.
And the one that escapes, it carries away a bit of energy from the black hole.
So it's like the black hole is slowly losing energy.
Exactly. It's what we call Hawking radiation.
Okay.
So black holes aren't completely black after all.
They're leaking energy.
They are. And over a very, very long time, they actually evaporate completely,
Black holes can disappear.
according to Hawking. Yep.
That's incredible. But Hawking didn't stop there, did he? He also tackled the arrow of time.
He did. That's right.
The fact that time seems to move in only one direction.
From past to future.
Yeah, like we experience this all the time. A dropped glass shatters. You can't unspill coffee.
Right.
We remember yesterday, not tomorrow.
Time marches on.
But isn't it weird that the laws of physics, most of them anyway, work just as well backwards as forwards?
It is a bit of a tussle, isn't it?
Yeah, like if you watch a video of a ball bouncing, you can't really tell if it's playing forwards or in reverse.
The laws of motion don't care about the direction of time.
So why do we experience time moving in only one direction?
That's the big question. Hawking explains that there are actually multiple arrows of time.
Oh.
Yeah. The one we're most familiar with is the thermodynamic arrow of time. It's the direction in which entropy increases.
Entropy, right. Remind me what that is again.
Entropy is basically a measure of disorder.
Okay.
Like, think of a messy room, right? It takes energy to tidy it up to decrease the entropy. But if you just leave it alone,
It gets messier.
exactly, it naturally tends towards more disorder, higher entropy.
So the universe is like my bedroom, always on the verge of chaos.
I like that analogy. And the second law of thermodynamics tells us that entropy always increases in a closed system.
Okay.
So that gives us the thermodynamic arrow of time.
So our experience of time moving forward is connected to this tendency towards disorder.
That's the general idea.
It's like the universe has this built-in bias towards messiness.
You could say that.
And that bias defines how we experience time. Pretty wild stuff.
It is. But didn't Hawking also talk about a cosmological arrow of time too?
He did. That's the direction in which the universe is expanding.
Okay.
And it raises a really interesting question. Why do all these different arrows of time, thermodynamic, psychological, cosmological, why do they all point in the same direction?
That is a good question. It's like the universe is conspiring to make time flow one way.
It's a mystery. And Hawking suggests that the anthropic principle might give us a clue.
The anthropic principle.
Yeah, the idea that intelligent life can only exist in a universe where these arrows of time are aligned. So we're only here to ask these questions about time because the universe happens to be set up this way.
Maybe. It's a possibility.
That's a really profound thought. Okay, I gotta ask you about time travel. It's such a staple of science fiction.
It is.
Did Hawking think it was actually possible?
Well, according to general relativity, time travel is, at least theoretically, possible.
Okay.
Remember how massive objects warp space-time?
Right.
Well, if you could create a strong enough warp, you might be able to bend space-time back on itself.
Creating a loop.
Yeah, time loop. But there's a big catch.
What's that?
Doing that would likely require exotic matter, stuff with negative energy density.
Negative energy. Is that even a real thing?
It's pretty weird, but there's some evidence that it might be possible, at least on tiny scales.
Huh.
The Casimir effect, for example, seems to...
Okay, so negative energy might not be just science fiction then. But even if we could somehow create a time loop, wouldn't we run into all sorts of paradoxes? Like, you go back in time and accidentally kill your grandfather before your parents are even born.
Yeah, the classic grandfather paradox.
Right.
Hawking explores this, and he suggests a couple of ways to resolve it. One is the consistent histories approach.
Okay.
It basically says that time travel is only allowed if it doesn't create paradoxes.
So, like, the universe has safeguards to prevent you from messing things up too badly.
You could say that.
It's pretty reassuring.
Another possibility is the alternative histories approach.
Okay.
This says that every possible history already exists on a separate timeline.
Whoa.
So when you travel back in time, you're not actually changing the past, you're just creating a new branch in this massive multiverse.
So time travel wouldn't be like rewriting history, but more like creating a whole new reality.
Exactly.
But if time travel is possible, even remotely possible, why haven't we met any time travelers yet?
Well, maybe they're out there just being very careful not to be noticed.
Lending.
Right. Or maybe there's something that prevents large-scale time travel. Hawking called it the chronology protection conjecture.
Chronology protection. That sounds serious.
It does. Okay, so in the final chapter, Hawking brings us back to the search for a unified theory of physics.
The holy grail of physics, right?
Exactly. Finding one theory that explains all the forces and particles in the universe.
But didn't we say earlier that general relativity and quantum mechanics don't really work together? How could you even unify them?
That's the challenge.
Yeah.
Hawking talks about some attempts at unification, like supergravity,
Okay.
which combines general relativity with the idea that every particle has a superpartner particle.
So it's like every particle has a secret twin.
Sort of. But supergravity has run into some problems.
Like what?
Well, it doesn't quite match up with what we observe in the universe.
Oh.
String theory is another approach.
String theory.
Yeah. In string theory, the basic building blocks of the universe aren't particles, but tiny vibrating strings.
Like little pieces of string.
Yeah. And different vibrations correspond to different forces and particles.
So it's like the universe is a giant musical instrument.
That's a great way to think about it.
Mm-hmm.
Now, string theory gets pretty complicated. It requires extra dimensions beyond the ones we experience.
Extra dimensions. Like more than up, down, left, right, forward, back.
That's right. But these extra dimensions, they're curled up really small, so we don't see them.
So it's like a hidden structure to the universe.
Exactly. String theory has some promise, but it's still a long way from being a complete theory of everything.
It sounds like there's still a lot we don't know about the universe.
There is. But I think it's amazing how far we've come.
I agree.
You know, from thinking the Earth was flat to understanding black holes, the Big Bang, extra dimensions.
It's mind-blowing.
It really is. Hawking's book, A Brief History of Time, it takes us on this incredible journey through all these discoveries.
It does.
It's a reminder that we're part of something so much bigger than ourselves, this vast, mysterious universe.
It makes you feel small, but in a good way.
I know what you mean.
So as you're going about your day, just remember, you're walking on a planet that's orbiting a star,
In a galaxy that's hurtling through space.
in an expanding universe that started billions of years ago from a single point.
And maybe, just maybe, there's a time traveler out there watching us wondering about the same things we are.
That's what the thought. Thanks for joining us on this deep dive.